Welcome back, everyone. I'm just looking over the chat, and it looks like there is considerable interest in learning more about distance estimation error and how that might impact inferences. So I think we're going to have two really important things to look at in the third hour of today. One is going to be this distance error, and the other thing is going to be movement of individuals. And maybe the two combined, because I guess in the field, birds are moving around and there is observation error. So really the combination of the two is what might not only lead to bias, but also more uncertainty in our estimates. And because it is also directional, so if things move close to us, then probability of detection increases. So kind of that's what introduces the bias, that they move around back and forth to the observer and away from the observer. But when they move away, we are going to be less likely to detect them. So that's for sure is a form of bias. And the distance estimation, that is more like a variance thing, but we'll see how these two combined are going to maybe cancel each other's effect out, but I doubt. We'll see. So right now we have still a few things to do before we can just go ahead and do all kinds of simulations in Shiny. I know all of you are waiting for that. But let's finish with estimating these distance sampling parameters so that we can talk about average detection, effective detection radius, and so on, so that as Dora was exploring and going to the tallest mountain, we'll have the same attitude, and we're just going to collect P and Q along the way so that we can put them together and adjust density and talk about our population size. So that's at the end of this remaining part of the code. So let's go back to it. So we talked about this Q average detection. You can see this familiar curve. And this is just, we can use this integrate function to integrate over this F that we defined up here. So if you know that function that you're trying to integrate over, then there is this numerical way of just doing that without any kinds of math, which is a really powerful feature of R and all kinds of similar languages. So F, our function, took distance and the tau parameter. Rest were just fixed, but you can play with the same kind of setup and integrate over a hazard rate function if you change these. And then you get G of D, which is the detection function multiplied together with increasing circles. So this age of D that we talked about. And you can integrate over to get the total up to this R max. We can set R max to infinity as well. Scroll back here. So this is what our F function was doing. So if we take the integral, that's how we, with increasing R max, this is how we can capture this curve. This next one is just going to draw these diagrams that we use to conceptualize all these probabilities. So again, our average detection Q refers to the black volume over the total volume of the cylinder. And here we have control over our max that's as big as we decide it to be. So this is nothing related to the shape of the function or like EDR. Now let's have a look at binned distances. This is when we take our counts and put them in distance bins. So if you imagine now we have 2 circles instead of just one, then you can count things inside this circle and outside of that circle, or maybe within different rings, kind of excluding what you already counted, going from the inside to the outside. And this is how you get the counts, because the counts are going to be proportional to this volume inside each of these bins. So finally, putting things together, this is the EDR that we talked about. And so this is the function I mentioned before, find EDR. So if we have whatever distance function, we want to be able to calculate the integral. Although this is an exercise question, but I'm just going to explain it so that we can move ahead. So what's happening here inside the function is that we define distance function times 2 times distance times pi. That is our area increasing. So this is the weighted distribution we need to be able to calculate the integral and as a result the volume. So this next line captures the volume through the integral. And then there is another function which then calculate EDR based on volume being equal to EDR squared times pi. Again, linking back to this concept of calculating this volume versus the outside volume. And if we equate the two, then we can see the distance is supposed to be 0. Where the distance is 0, that's where we find our root, which is our EDR. So this is what the function does. Let's see. Find EDR for tau equal 1. There's some numerical precision difference, but this is still pretty close. Tau 10, we're supposed to get 10. Tau 1, b equals 1. This is the negative exponential. Now you see, this is not the same number as tau. So that's why there's not a really nice link between the parameter of the distance function versus EDR itself. You need some kind of formula or a numerical integration to get to this quantity. It is not impossible, but it takes more effort. So it's 1.4 because the initial curve is going down faster. Now this one, tau equals 1, b equals 4, hazard rate function. That is again a different value than tau itself. And so far these implied unlimited distance. So the default was R max equals infinity. We can also think about EDR in the context of a truncated distance count. If I just scroll back up here, that means the total volume of the dough becomes not just the whole shape going out to infinity, but if you cut it 150 meters, then that is just going to put a bound on this total volume. But still, within that predefined R max, you can find an EDR which is going to make the outside versus the inside equal. And this is what we are looking for. And this handy little function is going to give us that for tau equals 1, for the half normal, if we have a truncated distance, EDR becomes something less than tau. This is another important thing to keep in mind, that this tau equals EDR only works for unlimited distance counts. If you have a truncated distance, then EDR is going to be something less. And finally, we have this cumulative density. And that is what we can use to bin the data. Now just think back what dA was. That was the distance to all of the individuals in the landscape, 1,013 nest locations, and their distance from the observer. Now we can put these into bins. So we have that data frame called DAT, which we had the distances, and now we have this binned data. And what we did, we used the distances themselves and breakpoints 1, 2, 3, 4, 5, and infinity, and also added 0 so that we get nice bins, and include lowest so that 0 distance is still counted. Table DAT bin. So we have 0 to 1, 1 to 2, 2 to 3, and so on, and 5 to infinity. So now we are putting circles around the observer, increasing the distance and counting all the nest locations inside each of these distance intervals. So this is what we get for the binned data. Again, we had that previous histogram which just showed all the exact distances. Once we have the binned data, we can still show them as a bar plot and show the corresponding probabilities that we will need to match. So now this goes into the model that we are going to use to estimate our parameters. We have the binned data, we have a model describing what probabilities should look like, and we are trying to match these two. So finally, we get to the last layer of our simulation, which is called BSIMS transcribe. And this is where we can take this input object O, which was, we did the detection, specify the distance function. So we have now total abundance, and out of those, slightly more than 1/10 were detected. And we haven't really specified in which way, and the default is just heard. So that's why we heard them instead of visually detecting them. So BSIMS transcribe takes a bunch of arguments. So if you look up the help file, you're going to see you can specify the time intervals, the radii, which is what we did here with the breakpoints, 1, 2, 3, 4, 5, and beyond. Error, which is something we'll come back to. Condition, again, we'll talk about it more. Event type, that is just going to inherit from the behavior layer. And perception, this is what we played with last time. This is the under versus over counting, how we perceive the distinct individuals. So let's just leave everything as the default, but specify the breakpoints for the distances. Now we get this TR object, which now says not just how many was detected, but also detected by breaks of 0 to 10 minutes. So there are no time intervals, and we have these distance intervals to talk about. And there is a table, which we can also say get table TR. That is going to give this breakdown that looks familiar from the Shiny app, when you have the time intervals as columns, distance intervals as rows, and the corresponding counts. So now if I scroll back up here, we had this table, distance, and the binned versions. So this is what really that transcription does, is we take the distances and put them into bins. And as a result, you're going to see these are the distance intervals and the corresponding numbers. So now we can take these numbers and put them in some kind of function that is going to estimate our parameters. Before we do that, let's just link it back to the cumulative density function. this is very similar to what we did for removal sampling. There, the shape of this was slightly different, and instead of radii, we had time intervals, but it was a very similar concept. There's a probability which goes from 0 to 1, and as a function of time or space, we can describe how that is going to increase if we bin the data. So we can relate these jumps to the number of counts we get. And because we then take the sum and divide everything by the sum, that means we are conditioning on the total count. Again, this is going to be independent of the true abundance. And the last piece of the puzzle is we need to talk about this availability bias. So with the previous simulation, we said, don't include any detectability. All the nest locations are as initial locations going to be available for detection. That is often not the case. And let's now include that. That means that the value of the distance function at distance 0 is going to be less than 1. So if we say phi, which was the singing rate, once every 2 minutes, that is half in every minute, 0.5, we keep tau as 2 and density is still very high, 10. So we have lots of numbers from a single landscape to play with. And then run pretty much everything as the default except for specifying density, phi, and tau. Let's see what we get. I have a really crowded landscape that looks like this. Wow. So you see now not just the nest locations, but also the dots, which means some behavior, at least vocalizations happened, not really movement because we haven't specified any movement there. And then we also have the detection on top of these as indicated by the black rays. So finally, we say, here are the time intervals, 1 minute intervals up to 5 minutes, and then radii as 50 meter, 100 meter, 150, and 200, which is going to make this truncated distance count. So we disregard anything beyond 200 meters. Let's do this. So we transcribe this landscape and this simulation outcome into bins, and we get the removal table. Now, instead of just distance intervals, we also have distance intervals and time intervals. So if we look at the sums for each row, then we get the totals for the for what we need for distance sampling. And if we look at the sums in each column, this is the data we need for the removal sampling. And we assume that these two processes are independent of each other. We are conditioning on the same total number of counts. If we plot this object, then beyond just the raise to the detections, we also see the increasing circles, and also there is this pale red shade. So if it would go to infinity, then everything would be this pale red. And also for the time intervals, this is not related to the space, just showing this is the total time duration, and we only counted up to 5 minutes. So you could change this and say, what happens if I only count to 3? What happens if I count to 8? And then also changing the distance bins, 50, 100, and nothing else, or everything beyond. So this is just a visual representation of the kind of sampling protocol that we put on top of the simulated landscape. So what we can do here is let's estimate density. So first we need to use the column sums and REM, that means our removal table. So this one here, rows, columns going for distance and time intervals. So if you take the column sums and create this little matrix from it, we get these column sum numbers, 21, 18, 14, 6, and 4. And as you recall, we needed another matrix, which is going to have the endpoints for the time intervals. And with C multi-fit, we specify it's a removal model. So we get that simple estimate, and phi hat is going to be our estimate for singing rate. Let's see how close we are. We used 0.5, it is 0.38. Not too bad, but it is also not perfect. So based on this, we can estimate this P, probability of availability, using the logic from before. So this is the cumulative density function for the removal sampling, 1 minus e to the power t times phi. And we use the maximum duration here, which was 5 minutes. That's how long we've counted. So not the 10-minute for the simulation, but just for the sampling event, 5 minutes. So this 5 minutes times our estimate, this is going to be the P estimate for probability of availability, 0.86 almost. So the next step is that we take the row sums from this REM removal table, like this 6, 11, 27, 19 here, and the corresponding matrix with the distance endpoints, 0.5, 1, 1.5, and 2, and specify the type as distance sampling using the same function. So now we have this model and calculate tau hat as e to the power the intercept coefficient. And we've talked about why we use the logarithmic link for phi for removal sampling. Here tau is again a non-negative number. So we can use log transformation to model it and then back transform it using the exponentiated version. So this is tau hat. Let's see how that compares to our original 2. This is 2.2. Calculate R max, which is the maximum of our bin endpoints, which is 2. R max is 2. And then we calculate Q. Instead of an integral, there is an analytic formula how you can do that. Tau squared over R max squared times 1 minus e to the power minus R max over tau squared. So this is very similar to the distance function, but there is a scaling involved. So this is how we get Q, which is 0.68. So now we have all the 3 pieces that we need to account for availability and perceptibility. We know the area that we are sampling over. And because our expected value of the counts was density times area times P times Q, we can rearrange this and get our estimate for density as our count divided by the product of area times probability of availability times probability of perceptibility, which is P times Q. And these little hats are there because that's coming from some data, and it is an estimate based on the parameter phi or tau. And area was known, that was 200 meters. So we know 200 squared times pi is our area. If this is the case, then we can just calculate this density estimate, sum of the removal table. So this is our total count, 63. And then this is our correction. A not found, of course. R max, that's the truncation distance 2. Squared times pi is our area, 12.56. So our correction is A times B times Q, 7.36. Let's calculate D hat and compare it to the true value. 10 versus 8.56. It's not perfect, but based on a single really crowded landscape, that's not too bad. And we are going to do more replication. It's kind of in real life, we have multiple point counts. The same idea goes here. If we have more replicates, we are going to get this estimate improved. So this was, again, the truncated distance case. Now let's have a look at the unlimited distance case. When we have this last endpoint as infinity. So the only thing is now we are going to repeat this line with new radii. And our removal table is going to be slightly different as a result. And the same goes for the sums. So now if you look at it, there's one more row added, 200 meter and beyond. We have still some counts out there because, as we said, this is a really crowded landscape, and we specified tau to be 2, which is, again, is just really large compared to the real numbers we usually get for most species. So that's why we get quite a decent number of counts even outside of the 200 meter. Now we can do the same things. Remember that if you want to do this and you have the chance of playing with limited, like truncated or unlimited counts, you need to include these extra individuals into your P estimate. So that's why we are refitting the removal model, because these counts are now different because we counted up to infinity, right? So we get another model, phi hat again. Same simulation, but a different transcription. Only the transcription layer has changed. It was 0.38 before, now it's 0.41. We're getting a bit closer to the true value that we've used. And our P estimate is not too much, but slightly higher than before. Same logic, I just use the additional counts, 38 for 200 and beyond, and include that into our matrix. Now it has infinity as the last breakpoint. Fit the distance sampling, calculate our estimate for tau, and compare it to the true value, very close. So this really helps in estimating things. And now, instead of having a known area, what we have is an estimate of the effective area sampled, which is A hat equals pi times tau hat squared. This is EDR because we were using half normal. Otherwise, you would have to substitute the corresponding effective radius that you get from whatever parameterization you're using. And then the same logic would apply. You could calculate the effective area sampled. But now, think back to the cookie cutter analogy. Within this distance, we assume that detectability is perfect, and outside of it is none. Which means our Q, which was the average detectability inside the cylinder, and now our cylinder is EDR as the radius. So we can take Q equal to 1, and instead of a known area and some Q that is less than 1, we now have Q equals 1 and the effective area sampled, which is an unknown, and that's something we estimated through the distance sampling model. So now the correction is A times P. Let's see what we get. Area hat, Q equals 1, and then sum of the new removal table, which is 101, and area hat times P times 1 is our correction, which is now going to be 11.36. So if we get this new estimate for density, it is somewhat larger. We had 8.4 something, as I recall. Now it's 8.8. So a bit closer to the truth, but it's still off a bit. So this is the two ways of how someone can adjust for the Q, like the detection process related bias, under a truncated distance count and then unlimited distance count. Sometimes these two are combined, and so what happens there is for each part of the data or each row in the data, when P and Q or even A hat might depend on site-specific or time-specific covariates, you can estimate these for each sampling event independently. And then if you have, in that case, an unlimited count, then you follow this logic. If you have a truncated distance, then you say, I know area times P times Q. So these two can be combined when you're dealing with real data sets. And just to do justice to the simulation, here is one. I'm not going to run it, but what this does is we do replication 200 times, the same settings as we had before. And I run this last time or last night, and this is what I got. So if you run the same thing, you're going to get the same exact results. And I had 0.5 tau as 1, not 2, and also more realistic density, 1 instead of 10. So this is not pack everything in a single landscape, but get something closer to what we would normally observe out in the field, but have it replicate 200 times. So based on the unlimited or the truncated distance cases, these are the estimates I got. For phi, it was very close. For tau, it was again very close. And as a result, our density, once we corrected it back, was again very close to the original simulated value. This just means that the default settings in our simulation are going to work according to the model that we specified for the QPAD methodology. This doesn't mean that the real world operates like that. And so that's why we are going to explore how things might be different. So before we go there, after the break, so we have plenty of time to play with the settings and see how different these results might get if we change the distance bins, add the distance error or movement of the individuals, and just see how this happens for the real data set, which is running this code so that we set up our data for the JOSM Alberta data set that we did before. We pick Tennessee warbler again. And so we have the removal sampling and the distance sampling related data set specified here. So we have this Y table for the duration. And what I mean by that is the removal sampling part. So this is our data, the different distance intervals, new individuals counted. corresponding matrix with endpoints of the time intervals. Then we have the distance sampling related data input, 0 to 50, 50 to 100, 100 and beyond. And then another D matrix with the endpoints 0.5, 1, and infinity. Once we have these matrices specified, then this is how we can get a removal model, as we saw before. And we're also going to make this as a function of time of year, or the scaled ordinal day. Because we saw that was pretty influential, so let's just stick with that good enough model. It is taking a bit longer than just a simulated landscape, because this has how many rows? Dim, Y. So 4,500 rows. So that's why it's taking a couple of seconds. Now we can print out the summary, which is going to say there's a negative relationship with day. That's significant, and we can use this line for prediction. So we take the model matrix. As you recall, that was just the intercept and this day. Multiply them together with the coefficients and then exponentiate it. If you do this, then it's going to be a matrix, and we don't want that extra dimension, we just want a plain vector. That's why we are using drop. So this is going to make a vector out of this matrix. So we get this summary. And this is strange. Oh, that might be because okay. I'll investigate later why we are getting a constant number. Let's just go ahead for now. Summary P. There might be very little variation. That can be why we see all these same numbers, but it's still weird. So maybe I just investigate in the break, but I'm not going to do that right now. So if we move on and do the distance sampling part, just a constant. Now we use the distance sampling related matrices that we saw before, and say type is this, which is going to be the distance sampling. Then we get our model, and we get this log tau value of minus 0.48. We can also try covariates that are going to influence how the distance function looks like as a function of forest cover or different habitat types. So now we have three models for the distance sampling, and we can do model selection using AIC. So now we have this little table, and we see model number 2 came up on top as the best supported based on AIC, and that happens to be the one with the discrete categories for habitat. So let's define this as the best model. You can see the summaries. There is the intercept. Then for deciduous forest, it's the intercept combined with a slightly lower number. And then coniferous, that's not very much different from the intercept. So we can again predict this using this matrix product notation. So to get the tau estimates, and let's plot it against habitat. This is our effective detection radii for the different open deciduous and coniferous forests. So I might stop here and wonder about whether this makes sense. In open habitat, you get 0.64 as your EDR, which is like 64 meters. In deciduous forest, you get close to 60 meters. And in coniferous, that's very close to slightly lower than the open environment. So here you have the skinny branches with not a lot of leaves rustling. So maybe that's what's driving these differences, that in deciduous broadleaf forests, you get slightly smaller effective detection radius. So it's not too outrageous with respect to the values that we are getting, and also the pattern makes sense. So let's see, how do we account for these biases? We calculate the correction as A times P times Q. So we have this corrected number as our new density estimate, 1.03. We can also use these correction values and the log of them as an offset in the GLM. So this is what we are going to do on day 4. We are not going to just look at the whole data set and calculate the mean count and adjust that to get mean density. We want to be able to predict density for each location given all kinds of land cover, climate information that we can get. So we're not just interested in the mean density over an area, but we're interested in how the density varies as a function of landscape characteristics or geography. And in this case, it's going to be much more useful to have this as an offset. And as you recall, offset is a term in the formula that we specify for GLM that we assume we know. So we are not going to estimate a coefficient corresponding to that. So now it is also clear that we need to then do removal modeling, distance sampling, come up with these quantities, A, P, and Q, based on what we can predict from these models and use those as offsets. And if we do that and specify GLM, family Poisson, and offsets equals A times P times Q log transformed, then we get this model M, and the intercept is going to be very close to this hand calculated average. So the mean density is going to be close, irrespective of whether you are using just the mean or a GLM. And the advantage is going to be that now we can specify something more than just the intercept. So for example, we can use forest cover, categorical land cover, and so on.